we're going to compare the continuous time signals with discrete time signals, and what are the differences that the discrete time signals have, and in particular how the complex exponential signals compare with the continuous time exponential signals. Now, there are many similarities between continuous time and discrete time signals, but there are also a number of important differences. So, in particular, uh, we, we, we're going to talk about the discrete time exponential signal, e.g. omega naught n. Now, we have already identified the following two properties of its continuous counterpart, that is e.g. omega naught t. Okay, so e.g. omega naught t is a continuous time complex exponential, while e.g. omega naught n is a discrete time exponential. With, if you recall that omega naught that we discussed last time, if you consider n as a dimensionless discrete time index, then omega naught has the units of radians. Okay, radian is a dimensionless quantity. It's a ratio of arc divided by the radius. So radian is dimensionless. But over here, since the time has a dimension of seconds, this omega naught of the continuous time exponential has the units of radians per second. Okay, so this is the first difference that you can just really see over here. The in the dimensions are different. So these are two different frequencies, and they exhibit different behaviors. Okay, so first of all, you see, if you recall in the discussion of uh, complex continuous time exponentials and sinusoids, because you can always express a complex uh, exponential in terms of sinusoid. Okay, so for example, the real part is the cosine, and the imaginary part for this exponential is the sine function with the same frequency omega naught. Okay, and no matter uh, um, what this omega naught is, cosine and sine functions are always periodic. Okay, but this is not true for discrete time sinusoids. Okay, so while e.g. omega naught t is periodic for any value of omega naught, this is not quite true for the discrete time sinusoid. For the discrete time sinusoid, the constraint is that omega naught by 2 pi has to be a rational number. That is, it has to be a ratio of two integers, let's say small m by capital N. Okay, so this, what we are going to do is we are going to see, we are going to derive this in principle from the basic facts of exponential signals. Okay, the other the first fact was that if you recall, this omega naught, depending on the magnitude of omega naught decides the or describes the rate of oscillations of the sinusoids, cosines and sine, or the complex exponential in the complex exponential um, continuous time signal, right? So higher this number is, that means higher is the rate of oscillations in the signal. But it's not quite true. If you go on increasing omega naught, that is in radians, for a discrete time complex exponential, if you go on increasing omega naught in discrete time signal, the rate of oscillations are not going to grow forever, right? That means omega naught is not quite distinct. Why? Because specifically, if you consider a discrete time complex exponential, with frequency omega naught plus or minus 2 pi, doesn't matter. Okay, so for example, if I have minus over here, then that means adding or subtracting 2 pi, this omega naught is not distinct. You're not increasing the frequency. So you see, the analytically, you can bifurcate this in two exponentials, right? And what is this? This is unity, right? This is 1. Therefore, and what it says is that adding or subtracting any frequency, any digital frequency omega naught that has that has units of radians, adding, I mean, increasing that frequency by 2 pi or decreasing this by 2 pi in transform in frequency domain, you end up having the same frequency. So this frequency is not distinct. Well, the point is that omega naught plus minus 2 pi is not distinct, is the same. This frequency is the same as omega naught. Okay, this fact holds true only in discrete time signals. Okay, this is not true. This is not true for continuous time signals or continuous time signal, this simply means you are increasing the frequency and you are increasing the rate of oscillations. Well, that is not true for discrete time case. Okay, discrete time case, these two frequencies are the same. These two frequencies are identically equal. Okay, so from the above equation, we see that the exponential at frequency omega naught plus 2 pi is the same as that at frequency omega naught, right? So omega naught plus 2 pi and omega naught in discrete time signals are same, which is not true in the continuous time case. In the continuous time case, you are simply increasing the frequency, but in discrete time case, you are where you are. I mean, going beyond. I mean, adding 2 pi or subtracting 2 pi is not making any difference, right? Because you're ending up in the same exponential signal, right, from where you started. So this frequency and this frequency has to be the same. So thus we have a very different situation from the continuous time case. This is the first difference, that in which the signal e j omega naught t are all distinct for distinct values of omega naught, right? I mean, if you change this omega naught over here, it doesn't matter by 2 pi or it could be any number. The frequencies are distinct. We are simply increasing or decreasing the rate of oscillations, and that means you're changing the frequency. But in discrete time case, you might not change the frequency unless we are shifting the frequency by integral multiple of 2 pi. Okay, so so the idea becomes like this. For example, if you now analyze discrete time signal in the frequency domain, and let's say since we know that the range of vision is fixed from minus pi to plus pi, right? Why? Because of this property, right? Because let's say this is the band in which I'm analyzing a signal, and this is not time domain. Okay, this is frequency domain. Let's call this omega, right? This is my frequency domain. Now, what happens is that whatever is true, let's say at this frequency, let's call this frequency as omega naught. Then omega naught plus minus 2 pi. So let's shift this whole thing at 2 pi. So at 2 pi, I'm going to have the same frequency. So 2 pi plus omega naught. This will be 2 pi. This frequency is going to be the same. That means the information that is contained within this band, within the band of 2 pi, is the same. If I shift this by 2 pi, or if I look at the same spectrum at minus 2 pi, the things are the same. I mean, the signal consists of the same frequencies. Okay, so it is sufficient to analyze the spectrum of the discrete time signal in the transform domain only between conventionally you do this from minus pi to plus pi, and you will see later on that for real-time signals the Fourier transform is both even and symmetric, which is the case over here, right? I mean, this is an even transform, right? So it's a real signal we are considering, but we are going to talk about this more in Fourier transform properties. But for now what I'm trying to emphasize is that your frequencies are not distinct. Okay, they are repeating. So it is sufficient to consider the baseband, which is from minus pi to plus pi, because at 2 pi, at minus 2 pi, and you see this scale can continue forever. At 4 pi, at 6 pi, the same spectrum is going to repeat. Okay, so the frequencies that are contained here, I mean, the bandwidth is going to be the same. This is the bandwidth. Okay, you have to consider positive frequencies only. Okay, so if I call this frequency to be call this omega h, the highest frequency, then omega h is the bandwidth. Okay, so for example, this is also omega h plus 4 pi. Okay, so this is the same frequency. Again, you're going to have omega naught over here. Okay, so this will be omega naught plus 4 pi. So the magnitude or the contribution, how much power does this frequency contributes, is the same, right? It's the same that you are looking at in the spectrum from minus pi to plus pi. Okay, so the frequencies are not distinct if they are separated by an integral multiple of 2 pi. So in discrete time, the signals are not distinct, as the signal with frequency omega naught is identical to the signals with frequencies omega naught plus minus 2 pi plus minus 4 pi and so on. So in discrete time case, this is the scenario. If you analyze the signal in for its spectrum, for for analyzing its spectrum, it's sufficient to look at the frequencies contained in the signal only from minus pi to plus pi. Okay, you don't need to go on further, because further beyond pi, beyond the this range of 2 pi, the frequencies are going to simply repeat itself. They'll repeat. Okay, so they're not distinct. Okay, so therefore, in considering discrete time complex exponentials, we need only to consider the frequency of the interval of 2 pi in which to choose omega naught. Okay, so any interval of 2 pi will do the job. So on most equations, I mean, you can analyze this within any interval of 2 pi. Okay, this is also interval of 2 pi, so this is the baseband of 2 pi. And then similarly, this will be from pi, 2 pi, and then there will be 3 pi. Okay, this is also an interval of 2 pi, right? So then from 3 pi, this will be 5 pi. So this is also an interval of 2 pi. Okay, so you take any interval of 2 pi, and conventionally, you will see that in the Fourier transform analysis, we are going to use either 0 to 2 pi or the interval minus pi to pi, because we know that the other intervals are just the repetitions of the baseband. This is your baseband. Okay, so all the intervals are just the copies. These are the copies of the baseband. This is your baseband. So baseband is where the entire spectrum is contained, and after that, the frequencies are simply repeating at integral multiple of 2 pi. But you see, this is only valid for discrete time signals. This is the first difference between discrete time signals and continuous time signals, that their frequencies are not distinct. Okay, I mean, you go on increasing omega naught, it doesn't mean that in time domain you are increasing the rate of oscillations. Okay, so the signal Ej omega naught n does not have a continually increasing rate of oscillation of omega naught, as omega naught is being increased in the magnitude. Okay, now this figure illustrates this idea. You see, if you have omega naught equal to 0 in part A, let's say omega naught is 0, then that means you're looking at a constant signal, right? It doesn't have any rate of oscillations. There is no rate of oscillations. It's a constant. So all the samples that they are taking the constant magnitudes. Okay, it's a constant. And if you compare this with the last depiction, part I, and to compare this with part A, now this 0 is separated from 2 pi by the interval 2 pi, right? So this thing repeats after exactly 2 pi, that we are getting the same signal. Okay, so this frequency 2 pi and 0 is basically indistinguishable in discrete time case, because this is separated by the interval 2 pi. Okay, so A and I are the same signal. Okay, this is the same constant basically. Now if you go on increasing the frequency, look what happens. If you increase the frequency in part B, so the initial frequency is pi by 8, right? So you have some samples and they're oscillating, right? Now you go on increasing the frequency. For example, this is pi by 4, so this was 0.125 pi. Okay, now this is 0.25 pi, and you see that the rate of oscillations have increased. And then you go on further increasing omega. This is 0.5 pi, and then up to pi. You see this is the highest frequency content that the signal can contain at around pi. Why? Because you see how much the samples are oscillating. At each successive sample, the sign is changing. So there are rapid fluctuations. Okay, so the sign is alternating. So this is the highest frequency that you can have, while 0 is being the lowest, right? So what happens? But now what happens if you increase omega naught thereafter? At this point, from this point, if you increase omega naught, well, this is 1.5 pi, and this is 0.5 pi, right? So let me put it like this. This is 0.5 pi. My omega naught is 0.5 over here. Do you see any difference in this case and in this case if you compare part D with part F? Okay, over here omega naught is 1.5 pi, and by how much this the difference is of pi, right? The difference is of pi. So these two signals are the same, right? These two signals are pretty much the same. Why? Because in the spectrum if this is the spectrum of the signal from minus pi to pi, we know that all these frequencies are going to repeat at an integral multiple of 2 pi and minus 2 pi, okay, and this trend is supposed to continue. Okay, so this is minus 2 pi, and then this is 2 pi. So this thing is going to continue. All right, now what happened before is, for example, let's say this is, we're looking this as at pi by 2. Okay, this is one frequency. So we know that this is also going to repeat at 3 pi by 2, right? So this was this thing was well, this is centered at pi. Let's center your focus, your attention over the center pi, which is between pi by 2 and 3 pi by 2. So pi minus pi by 2 is pi by 2. Pi plus pi by 2 is 3 pi by 2. Okay, so these two frequencies are the same. Okay, they are indistinguishable because they are contributing the same power. They contribute the same energy into the signal. Okay, so there's no difference in time domain. Even if you see the rate of oscillations are pretty much the same. Similarly, this is how much 7 by 4 is 1.75 pi, right? This is 1.75. So my omega naught is 1.75 in this case. Fine, this is not 2, but a little less than that. If it was 8, then 2. So okay, this is 1.75. Now, by what, by which figure can you compare this? So let's have a look if we can. Well, this is the one that that looks like the same, right? And it is in fact the same because if you can figure out, the reason is that omega naught in this case is 0.25, right? So omega naught is 0.25. That means over here, centered at pi minus 0.75 over here somewhere is pi by 4, right? Pi by 4. And then pi plus 0.75 will be somewhere here. This will be 7 pi by 4. So these two frequencies, again, they are the same, right? They are the same. They're contributing the same power. I mean, you can compare the levels of the frequencies. They are the same. The frequencies are repeating. So you see the rate of the oscillation. What is going on is that from the constant, as you go on increasing the angular frequency, which is in radians for digital signal, is, for example, over here this is 0.125. Then you increase it to 0.25. You see the rate of oscillations have increased. Then 0.5, it is still increased, and this is pi. Okay, so this is the maximum frequency. That's the maximum frequency. But what happens after pi is that the frequency decreases. Why? Because this figure and this figure, they are indistinguishable. Okay, so this part D and part F are pairing up, right? So the frequency is not increasing beyond pi, it's decreasing, right? So why it's decreasing? Because you are just repeating the frequency. 1.5 pi is 0.5 pi. There is no difference, right? Okay, this is 0.5 pi. So there's no difference. Okay, this is 1%. I've just I should have written pi over this figure as well, because these frequencies are indistinguishable. So you don't have any change in the rate of oscillations. Similarly, you can take a guess. I mean, this, for example, this figure in part H and part B, they are again indistinguishable. This is the same rate of oscillations. Okay, this is 0.125. Okay, and this is how much? This is 15 by 8. So 15 by 8 pi and pi by 8 are indistinguishable because they are having the same rate of oscillations, and they're again separated by the same amount, that is pi. Okay, so you're simply the point is you're simply repeating these frequencies. So what's going on is that beyond pi, you have decreased the frequency. Then the frequency go on increasing again, but then your frequency becomes 0 at 2 pi again. Okay, you again return back from where we started. Okay, because these frequencies are repeating. Okay, so any frequencies that are that are separated by 2 pi are just the same indistinguishable frequencies. Okay, so this is the difference. This figure illustrates quite in detail how the spectrum of a discrete time signal is different from that of a continuous time signal. Okay, and that the discrete time frequency, digital frequency, is only to be analyzed in the range of minus pi to plus pi, and it doesn't mean that increasing the digital frequency, you are increasing the rate of oscillations in time domain. No, you don't do that. Okay, it doesn't mean that, because frequency is simply repeating. So rather, as illustrated in figure below, as we increase omega naught from 0, we obtain signals that oscillate more and more rapidly until we reach omega naught pi. And this is exactly the highest frequency, because each successive sample is alternating, okay, which is much higher than this. For example, the frequency content is not much high. It's not changing the sign abruptly. Over here, it takes few samples. For example, it takes few samples before the samples they change the sign. But this is abruptly. Each successive sample is changing the sign. So this is the highest frequency. And then as you increase the frequency, you go beyond, because 1.5 pi is 0.5 pi are the same frequency, you decrease the frequency. So as we continue to increase omega naught, we decrease the rate of oscillations until we reach omega naught 2 pi, which produces the same constant sequence, omega naught equal to 0. So this and this sequence are the same, and both are constants. Okay. So therefore, the low frequency that is slowly varying discrete time exponentials have values omega naught near 0 and 2 pi, right? So this is slowly varying frequencies will be around DC. This is DC. This is a constant signal, and you can also have the same trend around 2 pi. Okay, so whatever is true at, for example, at 0 will be true at 2 pi. Okay, so around 2 pi and at 0, or at minus 2 pi, or at 4 pi, 6 pi, you have the low frequency content. But around pi, you're going to have a high frequency. At this point, you're going to have a high frequency content, right? So this is true for any other even multiple of pi. While the high frequencies, they correspond to rapid variations, and they're located at plus minus pi and odd multiples of pi. Okay, so let's draw this again. So what we said is that it is sufficient to consider the range of vision. Our range of vision is fixed for digital frequencies. So let's constrain our range of vision to minus pi to plus pi, and we know that the high frequencies are over here somewhere. Okay, so let's call this the highest frequency, omega h, and this is also minus omega h for an even spectrum x of omega. Okay, and this is the highest frequency, and this is around pi. Okay, the low frequencies will be around 0, and 0, you know, is the frequency of DC. Okay, that has no rate of oscillations. So note that in particular for omega naught equal to pi, or any other odd multiple of pi, this is the situation. Okay, if omega naught is pi, then that means it's simply minus 1n. So that means after each successive sample, each successive sample is going to change the sign, right? So for odd index n, this is minus. For even index, it will be positive. So the signal oscillates very rapidly, changing sign at each point in time. So this is the case. This is what's happening over here. So the sign change is happening very rapidly, and this is the most rapid sign change as compared to any other figure over here in this depiction. So pi is the highest frequency, okay, while 0 or 2 pi, or the frequencies around 0 and 2 pi being the lowest frequencies. Okay, all right. And again, I mean, just to, you see, the same trend is going to repeat itself at 2 pi. At 2 pi, you are going to have the low frequency content around 2 pi, which is the same at 0. So 2 pi, you're also having the DC. Similarly, at minus 3 pi, minus 2 pi, you're going to have the DC, and around plus minus 2 pi, you're going to have the DC content. But so you see, things they continue forever like this. But in the spectrum, you must remember that at odd multiples of pi, for example, this is 1 pi, then at 3 pi, around 3 pi, you're going to have maximum frequency. Similarly, at minus 3 pi, you're going to have maximum frequency. Okay, so such things, they continue because the frequencies are repeating itself in discrete time signals. Okay. Right, now the second property that we wish to consider concerns the periodicity of the discrete time complex exponential, which we have talked before as well. So you can watch some previous past two videos to understand this. We took some example as well. So if you recall, what we said was that if the signal is going to have the discrete time signal is periodic, then it must satisfy the relationship that if it undergoes the transformation of time shift, then it must satisfy the following relation such that you can find positive integer n that satisfies the given relationship. Now for a complex exponential, if it is periodic, then ej omega naught n should be equal to 1, right? Because you can again bifurcate this into two exponentials. So this should be equal to ej omega naught n. And if this ej omega naught n is equal to 1, well, then you have your discrete time complex exponential. You can say that it is periodic. So in order for the signal ej omega naught to be periodic with a positive period n, which is integer again, you must have the condition or equivalency. So what does this implies is that the constraint will be, so for the above equation to hold, omega naught n must be a multiple of 2 pi. That is, there must be an integer m such that omega naught n will be equal to 2 pi m. Okay, so omega naught n is basically an integral multiple of 2 pi, or equivalently you can write this as such. So what this means is that omega naught, your digital frequency divided by 2 pi should be a rational number. That is a ratio of two integers, m and n. So according to the above equation, the signal ej omega naught n is periodic if omega naught by 2 pi is a rational number and is not periodic otherwise. So these same observation also hold for discrete time sinusoid. For example, cosine of 17n is not periodic. Why? You can just see this is your omega naught, right? So if I just use this equation, omega naught divided by 2 pi is, there is no way that I'm going to get a rational number. Okay, I cannot express this as a ratio. So this is not going to be a rational number. Okay, rational number because of pi. Pi is not pi is an irrational number. It doesn't behave on the norms of rationality. Right? So it's not a rational number. However, if I take another example, okay, so let me finish this writing. It's not a rational number. So, however, if I have another sinusoid, that is, let's say cosine of 3, or okay, let's make this much simple, pi by 4 n. Okay, pi by 4 n. This is periodic. Why? Because for this omega naught, pi by 4. If I'm going to plug this into this equation, pi by 4 over 2 pi is a rational number, right? This comes out to be 1 by 8. And if you look this closely, this 8 is the period. We say that, okay, we can get a rational number, then what is the period? This is the period. Okay, and if you're going to plug this, okay, if I'm going to plug this for 8, 8 is my capital N, 8 is my capital N, okay, then what do I have? I have cosine of pi by 4n, this is pi by 4n, and then I have to add up another term, and that other term is your 2 pi. Okay, so basically this is cosine theta plus 2 pi, and again you can see that this is equal to cosine of pi by 4n. That's where we started. Okay, so this is indeed a periodic sinusoid. But for periodicity on the sinusoids, discrete time sinusoids, this is the constraint that omega naught by 2 pi should be a rational number. It should be a ratio of integers. And then if you found this out, then you should be able to find the period, and this capital N is the period. Okay. And what is the frequency? Well, you see the analogy is very similar. Omega naught by m is, if you want to rearrange the terms, it will be 2 pi by n. Okay, it's very similar to what we have in the continuous time case. Continuous time case, 2 pi by t was your fundamental frequency. Over here we have n. So okay, so this is for the continuous time case, and this is for the discrete time case. And you see the terms are very similar. Okay, So omega naught by m is your fundamental frequency, while for continuous 2 pi by t is, and for continuous time case it doesn't matter if omega is the rational number or not. T, because t, you don't need t to be an integer, right? T doesn't, it's not an integer. T could be anything. T could be under root 2. It could be square root of 3. It could be any irrational number, right? So or it could be in fractions, for example. But over here, n has to be an integer. N has to be an integer. Okay. So this is the difference. Okay. Now, so using these calculations we just made, we can also determine the fundamental period and the frequency of discrete time complex exponential, where we define the fundamental frequency of discrete time periodic signal as we did in the continuous time case. So if x of n is periodic with fundamental period n, then its fundamental frequency is 2 pi by n. Okay, so its fundamental frequency is 2 pi by n. So consider then a periodic complex exponential sequence x of n, which is e.g. omega naught n, where omega naught is non-zero. So as we have just seen, omega naught must satisfy the following equation for it to be periodic, because omega naught by 2 pi should be a rational number. Okay, that's the constraint for the periodicity, and that's the difference between the continuous time case as well, which is always periodic unconditionally. So for some pair of integers m and n, where n being a positive integer, if this comes out to be a rational number, then yes, e.g. omega naught n is periodic. Okay. Now, if omega naught is non-zero, and if n and m have no common factors in common, okay, then the fundamental period of x of n is capital N. That's exactly what we have seen. So if you consider this example again, you see that this is capital N, right? Because first, how we decided that this would be periodic is we just divided this by 2 pi and it came out to be a rational number, right? I mean, the idea is just to see if omega naught is a multiple of pi, because then this pi is going to cancel and you're going to end up with a rational number anyway. So this denominator consists of the period, and that's the capital N. And if you're going to plug this back, you're going to get back the original sequence. So this n is the period of the signal, because if it is periodic, then it has to have some period, right? And n is always a positive integral integer quantity, right? So using this fact together with the above equation, you can find that the fundamental frequency can be expressed as such. Okay, so if you rearrange this term, so this is quite the analogy is very similar to the continuous time case, where we have the continuous time frequency as 2 pi by t. Over here, this is 2 pi by n. The difference is that capital N and capital N is integer and capital T is could be fraction or irrational number. It could be any real quantity. Okay, any real quantity. So a real but positive. Okay. Note that the fundamental period can also be written as such. Okay, so this is the fundamental period, and we have to take the smallest period that defines the periodicity of or the of the discrete time sinusoid. Okay, because if for example discrete time sinusoid is going to have a period of 10 samples, then it's also periodic for 20 samples, 30 samples, but we have to choose the minimum. Okay, and this m is the integral multiple. M is again an integer multiple. Okay, so these last two expressions, this one and this one, again differ from their continuous time counterparts, because n has to be an integer, whereas t is not necessarily an integer, right? It's any positive real quantity, right? Okay, so now at this table 1.1 from your post text summarize some of the differences between the continuous time signal, exponential signal, discrete and the discrete time signal e.g. omega naught n. Note that as in the continuous time case, the constant discrete time signal resulting from setting omega naught equal to 0 as the fundamental frequency of 0, and its fundamental period is undefined. Okay, because if omega naught is set to 0, that means the signal is not oscillating. So we are talking of a constant. Okay, and constant has a 0 frequency. So this this column is for the continuous time case. Okay, and the other column is for the discrete time sinusoid e.g. omega naught n, and you can see the difference. So you see this omega naught is distinct signals for distinct values of omega naught, but over here we have identical signals having the same frequency of omega naught, if they're separated by the multiples of 2 pi. So that's the first difference. Then the second difference is that it is periodic. Unconditionally, your continuous time exponentials are periodic, while discrete time sinusoids are only periodic if omega naught by 2 pi is a rational number. Okay, and that rational number is m by n. So this is for some always true for some positive integer for n greater than 0, and m and n are integer quantities, or positive integer quantities. So the fundamental frequency over here is omega naught, while the fundamental frequency is omega naught by m. Okay, assuming that m and n do not have any common factors. Then again, the fundamental period for DC quantity is undefined. If there is no rate of oscillations, that means there is no you're going to define a period for that, right? And that's true for the discrete time case as well. So these are the similarities, while these are the differences in the continuous time and discrete time exponentials. Okay, so well, if omega naught is non-zero, the fundamental frequency is 2 pi by 0. If omega naught is non-zero, the fundamental period 2 pi by omega naught has to belong to positive integers. Okay, but however, in this case, in the last case, this does not necessarily have to belong to integers, right? This could be anything. 2 pi by omega naught could be anything. So it does not necessarily have to belong. So this are the differences and the similarities between the continuous time and discrete time sinusoids. So, but the things to remember for general analysis in signal systems of discrete time and continuous time sinusoids is that while all discrete time sinusoids, while all continuous time sinusoids are always periodic unconditionally, it's not true for the discrete time sinusoids. Discrete time sinusoids, their digital frequency omega naught by 2 pi has to be a rational number. Okay, it has to be a rational number in discrete time case. While in continuous time case, you don't need to worry. It's always periodic. Okay, so this must come out to be a rational number, and this capital N would be the period. Okay, in this case. So that's one, and the other that we talked was that for distinct signals in continuous time case, you're going to have distinct signals with different frequency if you're going to change the magnitude of omega naught, right? But if the omega naught in digital case, in digital signal, is changed by multiple of 2 pi, we're going to end up in the same identical signals having the same frequency omega naught. Okay, so basically omega naught plus minus, if I may write this 2 pi, and I can add an integral multiple of 2 pi, that's the k is an integer multiple of 2 pi, is still equal to omega naught. So these two are the same signals having the same frequency, two sinusoids having the same frequency in discrete time case having the same rate of oscillations. So they are not distinct. They are not distinct. Okay, so these are the two differences that one should keep in mind for discrete time and continuous time sinusoidal counterparts. Okay, that's all.